Okay. Then continuing on. So just talking about some of kind of examples for catalysts, and since that's not stepped right, let's just go ahead and add it all up there. If we look at the reaction of C2H4 plus H2 to C2H6, okay? First, let's just throw this question out here and see if you got this. What kind of reaction happened there? It's a couple different answers. I think I just heard someone mumble the one correct answer, which was not the one I was fishing for. It's a combination. So yeah, that's a good example for it. Any other ideas? You could start trying to look at the order, looking at rate laws for that chemical reaction. That requires understanding more about the mechanism, and we don't have context for that mechanism. We could look at the units of the rate constant to try and predict something about what the rate law would be, but we aren't given the units for the rate constant either. So predicting the order of this reaction is not going to go over particularly nicely. It's a reduction reaction, right? So if you remember, you talked a little bit about reduction and oxidation in 151. You're going to come back to it again in 152. And if you take OChem, it shows up in OChem as well. Okay, though in 151 and 152, we tend to quantify them a little bit more. In OChem, we just say if you add hydrogens, you're doing a reduction. Right? And if we're doing an oxidation, what did we do? You add oxygens. That's why we call it oxidation, as you're talking about adding oxygens. Okay, so in this case, it is a reduction reaction. We're taking that C2H4 compound, we react it with hydrogen to form C2H6. So we're starting with an alkene and turning it to an alkane. I can't believe I just said that out loud. Don't stress about that. The activation energy for this reaction is 100 kilojoules per mole. And then we get the rate constant to 10 to the negative 6 is where I would kind of jump to. This chemical reaction is incredibly slow, and it's not very efficient. So what we went out and did as chemists is tried to find reagents that would catalyze it, and it turns out platinum metal does a really good job of catalyzing this reaction. So we would take those same reagents, mix it with platinum metal, and then set it off, and we'd get our reaction, okay? Much swifter. You look at the activation energy, we're dropping by about half, okay? So that's pretty wicked, okay? And if we look at the rate constant, 10 to the negative 6 to 10 to the positive 4th. Right? If we look at the catalyzed reaction, we're looking at a reaction rate that's about 4 billion times faster. Right? So just mixing hydrogen with a carbon alkene does pretty much nothing. Okay? You mix it with platinum, you got product almost instantaneously. Okay? So our catalysts are pretty darn powerful, and they're something to kind of keep in mind and be aware of. Okay. Enzymes, okay, are catalysts, but from a biological system. So if we're looking at it, we're looking at evolution taking place to create these superstructures, and those structures then have particular activities. And so ultimately what I would kind of envision them as is you've effectively created a hand, a super specialized hand. Okay? So if I wanted to catalyze the ripping of this paper, okay, if I just left it out long enough, this paper towel will eventually fall apart into pieces, but it's going to take a bunch of time. Okay? So I could invent an enzyme, my hands, to grab hold of the roll, and the other hand grab hold of the paper, and I can tear significantly. That's effectively what our enzyme activity is doing. Right? Could we have built the enzyme to just tear? It didn't quite work. We need the enzyme to grab a hold of both pieces, or both aspects behind that. Okay, so when we're looking at our enzymatic activity, that's effectively what they're going through and doing. This animation makes it look a little overly simple, in my opinion, but what you're doing is taking this large superstructure and putting it into the enzyme. The enzyme is now effectively locking that structure into place so that it can't spin or move around. Water being free-floating in solution, that's the little red and 2 blue dot thing floating around, can now come in and interact in the exact location it needs to interact. Right? that speeds up the reactivity because you're increasing the likelihood of forming the correct orientation for the product reaction to happen. That's kind of cool.
So are catalysts largely an orientation compensator, or?
Depends on the mechanism. So some of them are orientation. I would argue, and I could easily be wrong, but in my experience when we look at biological catalysts, those are orientation. Okay? You're locking the structure into a particular orientation that successfully increases the speed of the reaction. Some enzymes get a little bit more complex, and it's not just orientation. They will actually start to stretch and bend the target molecule to get into the proper configuration as well. Okay? So they're actually changing the energetics of that system. Okay? That purple thing, okay, again, I said looks kind of simple. And what we're moving to is enzymes are a whole heck of a lot more complicated than that. And this giant tangle of blue, reds, greens, yellows, oranges, maybe some golds, depending on how you want to look at it, okay, is maybe, I'm going to bet based off that image, that it's a single strand. Okay, a single strand of what? Amino acids. This is a protein, and proteins are made up of individual amino acids. Those amino acids are linked together in a particular sequence, and it turns out when linked in a particular sequence, it'll change some of their shapes. Okay? If I organize some of them correctly, what will happen is that chain, if we look at that green part, will then start to helicize. Okay? But then the sequence breaks, and it's hard to see where the tail end of that goes. Okay? But the sequence of things that caused it to helicize isn't there anymore, and we switch to a different sequence. That change in sequence prevents the helix from forming, and the helix form breaks down. So what we're looking at is this massive tangle of things, okay? But that massive tangle of things can grab other molecules really well, okay? Or grab target molecules really, really well. Okay? How could it possibly grab them? What is it using to grab them? It's a hard question. Not 100% confident on where your content falls between 151 and 152. My understanding is the thing that's being used to grab other molecules is 151 content. Okay? You don't really get to experimentally play with it too much in 151, so you start off 152 lab actually talking about it. Your colligative properties, you're looking at intermolecular forces. It's the intermolecular forces, okay, the different polarities of individual bonds, both within the protein and in the target molecules. When those come into perfect alignment, you're now getting a strong interaction that can grab a hold and hold those things together. Okay? Similarly, with our paper example, if I had no fingers or thumb, okay, being able to tear becomes a little bit harder. That's less effective because the attractive force that I can exert on that system is now shifted. If I just add thumbs, I can now change how I grab, and that changes my ability to tear more efficiently. Biological systems, through millions of years, have effectively evolved fingers and thumbs through intermolecular forces that allow them to target things. My hand can target multiple different things. I can pick up the paper towels, I can pick up the pen, I can pick up my backpack. Most biological systems can't. They pick up one thing, that one thing only. Right? So we're made up of a sea of enzymes and proteins that are allowing us to navigate a lot of these complex chemical reactions. Okay? Based off of the lecture on Tuesday, I'm not going to play this video because if I try and play it, it's going to play and jump out, and then it's going to lock me out of being able to draw anything on the slides. Okay? So what I'm going to try and do is hopefully remember at the tail end of our class. We end at 11:15. I'll try and remember at 11:10 to double back to this and we can play this video. If we don't get to, I would highly recommend you do it. It's a short video. It's only 5 minutes. Okay? And what it's going to try and do is animate some of the processes of how an enzyme functions. Okay? And what is another name for an enzyme? It's a catalyst. Okay? It's just a biological catalyst. Oh, it's actually going to play. But it's going to play the audio through my computer. Pretty sure that's useless. Just listen real carefully.
Is a protein that catalyzes the chemical reaction. It initiates the reaction, speeds up the reaction's progress, and makes sure the outcome is always the same.
It's a little bit more involved than just a reaction. What did you say? Yeah, you are making and breaking bonds, yeah. Those are the individual mechanistic steps. Right? So when we're looking at that process, we looked at the overall reaction. It said it goes from this thing to the, what was it, cis-iconitase to citrate, something like that. Okay. That looked like just 2 steps. Okay. Well, those weren't 2 reaction steps. That was multiple mechanistic steps. And so if we're going to look at how that enzyme functions, we would have to break down each of those mechanistic steps, decide which one was the rate determining step, and then evaluate our rate law based off of that. So all those is someone studying that information to say what's happening and deciding is that a fast chemical reaction or a slow chemical reaction. Right? We push on that. They said acids and bases. When did you talk about acids and bases? OChem 1. When are you also going to talk about it? Or sorry, not OChem 1, Gen Chem 1. You'll talk about it in Gen Chem 2. You'll talk about it in OChem. Each of those acid-base reactions, we have to understand the fundamental aspects behind it. So we constantly study and represent that information because it's incredibly common to us. They mentioned histidine, serine. What are those? Amino acids. When are you going to learn about amino acids? If you moved into a biochemistry class. Right? That's when they'll start to push those. So what this is trying to set up is ultimately the grand scheme of everything that is chemistry. And your first 2.5 years of chemistry is building up enough content knowledge so that you can look at something like that. So I would argue that's a pretty cool preview into what you could work with. Right? That becomes interesting for some people that are probably want to become chemists. The people that didn't want to be chemists were like, well, I didn't really care. Right? Sorry. You get to deal with it anyway. Right? If we're going through and looking at an enzymatic structure, it can be complex. So sometimes what we'll do is look at simplified versions of it. And we see this weird globule-looking thing. That weird globule-looking thing is the protein structure. They've highlighted in blue where the part of the protein actually grabs a hold. Why is the stuff in white there if the only thing that I need is the blue part? Right? Simple enzyme. I have 2 hands that tear this apart, right? Simple. Why am I not just 2 hands? I also need the supporting structure to ensure that those 2 hands are in the proper space. Okay? I need the brain, if you will. It's not brain chemistry here. Okay? But I need the control behind that to allow that enzyme to function and do what it needs to do. Most of the rest of that structure supports that environment so that I can do the thing in the blue part. If we look at the beginning and end of these 2 images, what else do you notice? Right, here's something I noticed. This looks kind of U-shape, and then here it looks a little more O-shape. Why? It's grabbing hold of the individual pieces within it. As it grabs hold, it has to hold them in there so the chemistry can happen. Okay? So that's kind of a neat function behind our individual enzymes. What ends up happening when we look at the rates for these individual reactions? Okay, so we talked about rates. Can these rates now apply to this? So we heard, oh, it's a first order reaction. Is it a first order reaction? Does that look like the first order kinetic system? Okay. A lot of people will say no. Okay, and to that I accept. Does it look first order now? Okay, now it looks like maybe it is a little first order. So why is it changing? Why do you think the graph has these 2 different kind of interactions? This is a nice blue box question, so talk to the people in your group. For the record, I did give you this answer in our earlier lectures. So now it's trying to come up that information, pull it back up. So when walking around, I'm hearing people, oh, well, the enzyme can only act so fast, okay, which isn't necessarily a bad statement. But if you're making the argument, well, the enzyme can only react so fast, really all you're discussing is orange versus red versus blue on this curve. You aren't explaining why the blue has leveled off. Because yes, the rate of the enzyme does affect the curve, but why is the curve leveling off?
Is it because there aren't enough enzymes at a certain point?
There becomes the key line, is it's not just the rate of the enzyme. That's describing the steepness of our slope. Why does it level off? It's not just the rate anymore. I'm looking at in comparison to the reactant. How much reactant do I have in comparison to the enzyme? It starts to level off because what has happened?
It's running out of reactants.
Reactants are continuing to increase this way. I can't run out of reactants.
There isn't enough enzyme.
Yeah, it's the flip. I've run out of enzyme to grab the reactant. So that inflection point, and I'm sure we could do mathematics to find a better inflection point than what I've just marked, but where we're going effectively first order to now zero order is where the concentration of, or the amount of enzyme, how do I want to do that? The concentration of enzyme is equal to the concentration of reactant. As I continue to move higher concentrations of reactant, I've now exceeded the capacity for the enzyme. The enzyme can't turn over anymore. So I now have a new kinetic system. I'm looking at just the transition of the reactant to the product on its own. That first part is all enzymatic. This second part is now just A to product. That's why we see a difference in those two systems. You've overwhelmed the capacity for the enzyme to continue to function. So it is related to the enzyme, but it's related to the amounts of each of those individual species. That's what's controlling this.
So it's not an asymptote where it's like getting really close to it. It is quite literally just zero slope.
I think technically it's an asymptote.
Okay.
Yeah. That's pushing into the biochem class that there's a reason why I stopped teaching it, and it's because I didn't want to deal with any of this.
Yeah.
Thanks, Dr. Schneblin, for bringing me back into it. But yeah, I believe technically it's an asymptote because you can still transition from A to product, but that rate is going to be incredibly slow. So in comparison, it looks like it's a flat line, but I think what's actually happening is it's approaching the max speed we can get for the just the simple turnover. Kind of cool. So this is where we talk about some nuclear reactions. Okay? And I want to point out at this stage, I would make the argument, and I think I'm correct, based off of reviewing the remaining slides left, that we have covered all of the content for quiz 1. It's all done. Okay? There might be a little bit on the nuclear reactions side, and we'll talk about that when we get to it. Okay? But what nuclear reactions, as best as I can tell, okay, is now pointing out examples of how we can use kinetics to explain something. Okay? And we can also use that to say, well, why would we look at nuclear reactions? Okay? So what's happening with nuclear reactions? What happens with most of our reactions? If I take A plus B and I turn it into products, what happened? We're going to be nicer. Turn it to A bond B. What happened? Electrons were shared from one atom to the other. That sharing of electrons made a new bond. Okay? We can look at the system where, well, that's A plus B, Mike. That's a second order reaction. Well, we could shift to a first order reaction where it splits into A, like that. We're looking at breaking that bond. Okay, now very graphically showing how we've broken the letter A apart into two pieces. Kind of make sense? Okay, even then, that's how the electrons within A were redistributed to produce the component pieces that made that structure up. So most chemical reactions that you will study have to do with how electrons move, shared, okay, transferred from one place to another. Nuclear reactions are entirely different because it has to do with the nucleus. That's why I call it nuclear reaction. Okay. Well, what's in the nucleus?
Protons and neutrons.
Protons and neutrons. Electrons are irrelevant now. All we care about is what's happening in that nucleus. Right? This is why, if you go all the way back to early 151, you saw a notation something like this. With the, it says mass number, and we had atomic number. Right? And we had the symbol. Does that vaguely ring a bell? Okay. That was called atomic notation. I would argue that's not atomic notation, because atomic notation should take into consideration protons, neutrons, and electrons, because that makes up an atom. This isn't atomic notation, this is nuclear notation. Because in this notation, what do we call attention to? The mass number. What's the mass number? Half of it, right? Yeah, there it is. Protons and neutrons. What's the atomic number? Just the protons. So this notation isn't making explicit any reference to the electron balance within this system. It's being used specifically to reference the nucleus. Well, why would anybody want a notation to specifically reference the nucleus?
For nuclear reactions.
For nuclear reactions. So when we're talking about kind of the birthplace, and this is where this notation is typically brought up, we're talking about how we discovered atomic structure. And we talk about atomic structure, what's one of the biggest discoveries that we bring into it? The atomic bomb. Okay, that's where all of these things came about. And so while people were trying to study the energy releases associated with atomic bombs and exploding things and releasing tons of energy, what they were concerned about was what was causing that, and that's all nuclear chemistry. So all of the notations that are dissolved or divined around that point have to do with nuclear notation because they're concerned about blowing stuff up. Okay? That's the point. So when we look at those notations, they're trying to quickly call attention to that so they can look at that number, that mass number, and be like, boom, that's going to explode. Okay? They don't care how it chemically reacts, they care how it explodes. Okay, so that's changing your viewpoint on the structure, which then changes the language that we'll go through and use to discuss it. Make sense? Okay. That reaction, okay, when we're changing our nucleus, can happen either slow or fast. What's going to dictate it? Well, the element. Okay? A little bit. What about the element is going to dictate it? What things are in the nucleus? Protons and neutrons. So what's going to dictate whether it's slow or fast? Was that a favorable balance of protons and neutrons? Or was that a disfavorable balance of protons and neutrons? And the more disfavorable it is, the faster it goes. Okay? Do you need to know what makes favorable and disfavorable? The hardcore specifics, no, so don't stress on that. Okay? But that's where that kind of content is coming from, what we're kind of addressing and thinking about. Okay? So within our isotopes, we've got two isotopes here. Okay? What isotope do you think we're looking at? Shouldn't have taken that long. Come on. Lithium. Okay, good. How do we know we're looking at lithium? It says it. Good. Okay. Make it harder. Don't read the words. What isotope are we looking at? 3 protons, we're looking at lithium. Or, well, actually for the first one, red or green, we don't know what they are. So it's either 3 protons or 3 neutrons, or 3 protons and 3 neutrons. Either way, we're getting to the same element. Okay? So we'd be looking at lithium. Okay? So in this first case, we've got lithium-6. This notation written out this way. What does that notation mean? What does it mean when we say lithium? Okay, I like that. Okay, how do you know lithium means 3 protons? True, if we change the protons, we change the identity of the element. How do you know lithium meant 3? Yeah, there it is, the periodic table. We look at the periodic table, and the atomic number for lithium, Li, 3, we know lithium has 3 protons. So just having that word there gives us some information. That word tells us we have 3 protons. Okay? It also tells us we're looking at an element. Because if I said hippopotamus 6, you know you're not looking at an element, or an elephant. You're not looking at an element. Hey, that's why I said elephant. Make sense? What does the 6 mean? Right? Could it possibly mean the protons? No, because we already said the periodic table said the protons was 3. So what does the 6 mean? It is the mass number. It's not the atomic mass. Okay? It's the mass number. And this gets real nasty. Atomic mass is what we find on the periodic table. So we would look underneath lithium and it says 6.94. That is the atomic mass for lithium. How is the atomic mass different from the mass number?
It's an average of all the isotopes.
There it is. Okay? The atomic mass is an average for all isotopes. When I go through and say mass number, that's the mass number for that isotope and that isotope only. And as the mass number, that's now very easily defined as the number of protons and neutrons. So if lithium tells me I have 3 protons and 6 is my mass number, I can now do a quick calculation and know I have 3 neutrons. Make sense? I could also go through and look at lithium 7. How does that change? I add 1. Okay, there was an easy answer. Add 1 what?
Neutron.
Add 1 what?
Neutron.
Neutron. Okay, I thought you said charge. I add 1 neutron. I can't add a proton to increase the mass, because if I add a proton, it's no longer lithium, it's beryllium. Cool. Good flow off the periodic table. I like it. Okay, so now the next part. Write our isotope symbol for lithium 7. Dr. Schneblin likes to call it the isotope symbol. That makes sense. Okay? Typically, most textbooks reference it as the atomic notation, okay? Which I also disagreed with, and I called it nuclear notation. What would be the isotope symbol or nuclear notation for lithium 7? If we don't remember it, that was literally like 5 minutes ago. We just walked through what it was. Just wrote down all that information. It's easy to forget. I know. I say a bunch of stuff, and you're like, half the stuff you say isn't useful. Okay? Now you got to remember the other half of the stuff that I said was useful.
Well, it's because normally you just fire.
So, for our isotope symbol, we've got the element. We have to define that, so that's visible and easy to see. And then we have to define both the mass number and our atomic number within this notation. So that's 2 pieces of information that we have to somehow address around our symbol. Okay? So do we address it this way? From what I've seen so far, people who actually wrote down answers, half the class is being like, I sure hope you don't show it that way. And the other half of the class is saying, I sure hope you do. Who was this notation written for?
Nuclear chemists?
Nuclear chemists. And nuclear chemists wanted this information so that they could look at it and they could say what? Boom or no boom? That's it. Those are your choices. Okay? So if we're concerned about boom, do you want to see your information fast or slow? Fast. So when we read, as English speakers, where do we start our reading from?
Left to right?
Left to right and top to bottom. So if I read this, the first thing I encounter is
3.
3. Does this give me information about boom? That 3 is telling me the amount of protons that lithium has. Which isotopes of lithium will have 3 protons? Every single one of them. So is putting the 3 there particularly useful? No. And if I'm concerned about boom, the number I want to see is that 7, the combination of the neutrons and the protons. The atomic number I'll put underneath it. The atomic number arguably is redundant. Because if I do this, you can tell me how many protons it has. Why? Periodic table. And because you all are chemists, whether you like it or not now, you will always have a periodic table. So the atomic number is redundant information. Okay, so the first thing we want to be able to see is that mass number. That mass number should be written in the upper left-hand corner. And we now have our isotope symbol. Okay, that isotope symbol sometimes will frequently drop the 3 because it's redundant. I don't need it there. Kind of make sense? Cool. So how does this apply? Okay. Some isotopes are unstable or radioactive. Okay. And so what we're looking at within this plot, okay, is the number of protons versus the number of neutrons. Okay. And if we look real low, you'll see these kind of black things. Those black things represent stable isotopes. We call them nuclei. That word that I'm not going to pronounce. Isotopes. Okay, so the black ones are stable. Everything else has some instability with it, okay, or it's unknown. Okay, and what they've done, if you look, it's like a grid pattern, because that's literally what they did. They gridded it all out. Okay, so out here in this white space, why would we not know about it?
It either doesn't exist or hasn't been discovered.
We haven't discovered it yet to make any statements about it. Why have we not discovered it? What's that? Yeah, it's so unstable. Okay? So if we're looking at this, what we note is this kind of black line that moves through, and that black line looks really close to the solid black line, right? What is that solid black line representing? 1 for 1. Proton to neutron, all the way up. And if we look, the black stable line gets kind of close to that. It starts to veer off the more protons we get. Okay? Well, why would it make sense to have 1 neutron for every proton? What's the role of the neutron?
To stabilize the power of each other's particles.
How is it stabilizing it?
They buffer their repulsive forces.
They buffer the repulsive forces. They're effectively acting as a glue. Okay? So for every proton I've got, we would expect 1 neutron. Is that true? What element has 1 proton?
Hydrogen.
Hydrogen. How many neutrons does it have? 0. Why? What was the point of the neutron?
There's nothing to buffer.
The buffering of repulsive forces. Hydrogen doesn't have a repulsive force. We don't need neutrons there. As soon as we move up to helium, now what happens? I have 2 protons. I need something to buffer that repulsive force. Okay? How much? Okay, becomes a different question. And now what we're drawing is observationally based off of this. Why? Okay? Could we drill into that and say, why do I need 1 proton and 1 neutron? Yeah, we absolutely can. You know who's going to drill into that? Anybody that wants to become a nuclear chemist. Do you want to become a nuclear chemist? Then you just need to know this 1-to-1 ratio is pretty awesome. Okay? Kind of makes sense? The more we veer from that 1-to-1 ratio, the more likely we become radioactive. Okay? And if we go through and look at the options, what we'll start to note is what type of reactivity we're getting. Because what we've done is built a nucleus that's unstable. And so what it wants to do is somehow find its way back to that black line. Well, how can it do that? Well, if we're orange, let's just think about this. If we're orange, what does that mean?
It means that the isotope will decay via.
So that's cool. Pause. You're reading the table. That's I love reading the key of that. That's fantastic. That's awesome. I don't want you to do that. This is great. I love it. What does it mean to be orange?
It's unstable
Okay, why?
because it is off of that black line
How does it get to the black line?
through decay.
What decay? Now you're like, oh, you erased that. I don't care what it said over here. I want you to explain how can I get back to that black line?
It loses.
What is it going to lose? Okay? If it loses neutrons and I'm here, what happens? So for the sake of the recording, here we are, purple spot. Okay, cool. Right. If I lose neutrons, what happens? It goes down. Did I get more stable? Ah. So do I want to lose neutrons?
No.
No. What do I want to do?
Protons.
I want to lose protons. And that's a hard reflex. We're like, I don't want to lose protons. It changes the identity of the element. That's why it's nuclear chemistry and not regular chemistry. We're changing the identity of the element when we talk about these decays. Okay? Does that make sense? What if we're in the blue section?
Do you want to gain protons?
Could we possibly gain protons? Okay? But to gain protons, where do I get a proton from? That's a hard question. Here's my radioactive thing. I want more protons. How can I get more protons to it? I have to throw something at it? That's not saying it's unstable on its own. That's saying something else has to come in to stabilize it. If it's unstable, how can I get more protons? That's where what we would do is look at what those forms of decay are. And it's not going to be throwing something at it necessarily. It's going to be how can we rearrange those subatomic particles of protons and neutrons and turn them into other things. For instance, how could I gain proton? What if I lost an electron? Wouldn't that increase my positives? Yeah. Do I have electrons in the nucleus? No, so you can't do that. But the nucleus can rearrange its matter to eject effectively an electron. What? Yeah, that's kind of neat, isn't it? Okay. So what we're talking about is how it can navigate that and what are those possible processes. So if we go through and look at examples, there's two most common ones. We have alpha decay and beta decay. So in alpha decay, what's happening? Unstable nucleus changes its identity. Cool. How does it change its identity? What did the alpha particle, or what did the alpha decay do? As a hint, there's a symbol over there with an alpha next to it. What happened in alpha decay? So we could, real good, but slow you roll a little bit. It ejected an alpha particle. Yeah, that works. So we could call that alpha decay an alpha particle. That alpha particle, we know some information about it. We know what about it? It has 2 protons, and we know that because we followed our atomic notation or our isotope notation. The atomic number is in the lower left-hand corner. It has 2 protons. What else do we know about the alpha particle? Flashing gang signs over there. We got 4 is its total mass, so it would have 2 neutrons. Right? So we could push on that further. What is an alpha particle? What is the alpha particle? What thing has 2 protons and 2 neutrons? Helium. What we're ejecting here is a helium. A helium what?
Helium-4.
A helium nucleus. Does it have any electrons? No. Okay? There's no electrons associated with this helium atom. Because it's not a helium atom. What is it? It's an alpha particle. Kind of, sort of? What's happening in the beta decay? What's the mass of the beta particle? Let's go with the easy one. Where's the mass represented? Okay. That was a lovely answer 10 seconds ago. Now you got to answer my other question. What's the mass? Where's the mass specified for my beta decay? Top left corner. Boom. Okay. So the mass of the beta particle is 0. Okay. What contributed to the mass number? What contributes to a mass number? Don't tell me it's 0. I don't care what the number is. What things would I put to get me my mass number? Protons and neutrons. If I have a mass number of 0, how many protons and neutrons do I have? 0. There are none. Okay. What was the lower left? What was that supposed to be? That was our number of protons, right? Our atomic number. Can I have -1 protons? No, because what is the beta particle?
An electron.
It's an electron. Okay? So the notation looks wonky because what we're effectively doing is ejecting an electron. From where? The nucleus. Did the nucleus have electrons? No, but what we ended up doing is converting another particle into something else which caused the ejection of an electron. That's wicked. How and why? Take a nuclear chemistry class. Okay, I'm sure it's fascinating and neat. Has anybody worked on a nuke? Not on a nuke, sorry. Different statement. I needed to finish that word. On a nuclear submarine, I've had some nuke sub students that have known some more information about this. Did you say yeah?
My cousin did.
Your cousin. So I talked to them about it. They might know. They might also just know not what to touch, right? Okay. Depending on where they're at within that system. So our beta decay is effectively the ejection of an electron from your nucleus. The alpha decay is the ejection of a helium nucleus. Not a helium atom, so there's no electrons. Okay, and that's why we can't write helium here, because if we write helium here, that's now going to imply something about the electrons in the upper right-hand corner. Okay, and we're not implying that. That's why we call them alpha and betas. Okay, we'll sometimes call it decays. Why do we call it a decay? Because there's a particle that's emitted from this structure. We could go through and look at the alpha one, and the alpha one would make a lot of sense for decay, because what happens to my numbers? They decrease, so it makes sense. If I'm decaying, I'm falling apart. Does it make as much sense for the beta decay? What happened to my number in the beta decay? It stayed the same, or increase. That doesn't quite fit the decay statement as much as we would like, right? Okay, so here's a good review. Determine the rate law and rate constant K for the beta decay of krypton 89. Okay, good place to start. If we want the rate law, what should we be writing? Rate equals K should be an immediate reflex. Now what? The reactant, concentration of our reactant, which is Kr, also known as krypton. It's a little more fun if you use the name instead of just saying Kr, but okay. We could drop in those other numbers. I personally would not drop in the isotope notation, because those numbers, I think, would confuse me later on. Okay? And since there's only one Kr to worry about, I don't have to do it. What else do I need to specify within my rate law initially? What's the order of the reaction?
First order,
How do you know it's first order?
there's only one reactant.
There's only one reactant. What have you assumed? That you're looking at the mechanistic detail. You are not allowed to assume that, particularly when given a system that tells you the concentration and rates. What do you need to do? You need to solve for what the order is. Beside the point. Okay? So now it's a question of going back and reviewing all of your content process. Some of this can happen in your head, but we want the rate law, the rate constant K, at least figuring out how you would set it up. Oh, and that's it, because then the rest of it is just a description of what's happening, and that's our reaction. Kind of make sense? Okay, start working on it. Okay, so when we went through and talked about this, okay, we went through a couple different stages. At first, we just went through and did simple comparisons. Okay, and at least my walk around, it seemed like everybody got the simple comparisons. Okay, and then when the numbers started to change, instead of doubling, it tripled. Okay, everybody freaked out and couldn't figure it out, but it was the same ultimate system. Okay, and really what we went through and did is that we said the rate for one experiment over the rate for the second experiment needed to equal, I can't write, needed to equal the concentration of krypton for the first experiment to the x, concentration of krypton for the second experiment to the x. We could simplify that out, Kr1 over Kr2 to the x. If we've got this equality, now all we have to do is look at my experiments and say what changed. So I got a lot of you, I compared experiment 1 to experiment 3. Cool. Could you do 1 to 2? Could you do 2 to 3? Yeah, with only one reaction, you can make whatever comparison you want. So you're picking 2 and you're comparing those experiments to see what changed. Okay? Well, if we look at 1 to 2, did I do it? Stupid halves again. We can go 3.66 times 10 to the minus 5, rate 1, over rate 2, 1.83 times 10 to the negative 4. Okay? In that system, right, like, I don't know how to do that. You got a calculator, just punch buttons in a calculator, do the division, and see what the calculator tells you. I think it's going to tell you 0.2. Okay? Also known as 1 over 5. So for people that were going, it increased by 5 times, 1 over 5 is the same thing as 0.2. Okay? What happened for the concentration of the krypton? Well, we do the same thing. We do 0.1 over 0.05. That one's a little bit more straightforward. We could bust out in our head, and that's 1 over 5. What does the x value have to be to make this long equality true? It has to be 1. Which means I can go back to my rate law. I knew I erased something. There's my equals. And that x has to be 1. Right? And for anybody that's like, but bro said that over here. He said it was 1, and you said he was wrong. No, I did not. Okay? I said how he got the 1 was wrong. And that how becomes very, very important. Because if you're just pulling coefficients straight out of your equation, depending on how the test is organized, I would bet half the time you'll be wrong. If you're just pulling coefficients straight out of the equation, when we look at the Alex homework, I would bet 90% of the time you're wrong. Okay? You can't pull the coefficient straight out of the equation most of the time. When can you? Because there's one time that you're allowed to do it. Someone started to say it, and then one step. Give me a little bit more information than that. What is the step in reference to?
The overall reaction?
Nope. Remove overall reaction from your vernacular. You cannot take the coefficient from the overall reaction. You cannot. It is wrong.
So it's an elementary reaction?
It's your elementary mechanistic step. So step was a good key word because that's what we talked about when we went through it. If you don't remember that, the lectures are recorded. Double back. Look at it. We said the big signifier that helps us be able to pull the coefficients out is when we know it's a mechanism. How do we know it's a mechanism? It says steps. Okay? So your memory for steps was great. I just wanted to hear the mechanism part of it. Does that make sense? That's how we build that out. Once we know what our rate law is, now how do we solve for the rate constant?
The rate divided by the area.
Yeah. We could rearrange this equation, K equals rate over KR. Which rate? Any rate. Which KR? Cool, good answer. Okay? I can pick any rate I want, but once I've picked that rate, I better use the KR that matches. Okay? Does that make sense? Someone crunch that number? I know somebody did. What was the number for K?
3.66 times 10 to the negative third.
Okay? 3.66 times 10 to the negative third. Okay? If you haven't number crunched, you now have something that you can go through and number crunch and verify that you know what you're doing. Okay? You've got to check against it. Okay? Is this the rate constant? I was like, yeah, it's the rate constant. I'm actually going to say no. Sort of to be a jerk, but sort of because it's actually flawed. Yeah. We need to drop those units into the system. What do the units need to be on that rate constant? Seconds? Inverse seconds. Okay, so we can do that -1. Again, I don't like that notation personally. That's your choice. Okay? What doesn't make any sense? Inverse seconds is the same thing as 1 over seconds.
Right. I mean, like in math, it just doesn't, you never see that. If you divide meter like miles per hour or like miles, you get hours.
Well, what is miles per hour? Miles, inverse hours. And people are like, that looks stupid. Why would you write it like that? Yeah, we wouldn't write it like that. We would write MPH. What the frick does P mean? That means the per. Okay? Why do we not write it miles/hours? Because we could do that too. We could do /seconds. Okay? I would argue pretty much all of these have the same kind of inherent flaw. It's really hard to see whether you're referencing the numerator or the denominator. Okay? I personally struggle with that. I refuse to use those units, and I'll use this. Okay? You don't struggle with it, but good for you. Stop showing off. Okay, or show off more. That's fine. Okay? I want to see that unit so that I know what I'm doing with it later. Kind of make sense? Okay. We said 15. Let's just poke a little bit. Let's just see what else is out here. Kinetics of nuclear reactions. Okay, so if we look at our alpha and beta reactions, they will follow first order reactions. Does it make sense for them to follow first order? We just solved it and said, yeah, it did. But does it make sense? What's happening when we talk about nuclear decay? What causes nuclear decay? What causes nuclear decay? The nucleus. Okay? So if I'm going to think about these kinetics of these reactions, what do I need for that reaction to happen? I need a nucleus. Okay? And I need that nucleus to just be like, this sucks, and break apart. Which means that's a first order reaction. Okay? It's just naturally going to fall apart on its own. It doesn't need other particles in most scenarios. Okay? There are other forms of decay that might need other particles to initiate them. Right? So we could look at a kinetic system like we've seen before, our concentration versus time, and we could start to now add some more information behind this. Okay? So if you're an old school gamer, you may have heard of half-life. What is half-life about? Killing aliens.
It takes for half of the atmosphere, yeah.
Okay? Half-life is the amount of time it takes for half of your concentration to disappear. Okay? So it's a time. Why do we care about the time? Well, if I said there was a nuclear bomb under you, are you going to be a little upset? Yeah, okay. Okay, well, what if I told you that nuclear bomb decays not releasing a bunch of energy, but in a matter of seconds. Like poof, done. That's less of a concern. Okay? So the speed at which these things fall apart changes our interpretation of how dangerous potentially they are. Okay? Also in conjunction with the energy released and all that other stuff. Okay? So one of the things that we'll do is quantify half-lives. Okay? So I could go through and look at this. I've got the blue curve and the green curve, right? Okay, they both start at the same point at the top. If I want to go half of the concentration, where do I need to go?
Right with time.
I didn't talk about time at all. What are you going to say? What are you going to say time to? In the middle of what? In the middle of the concentration, right? Is that close enough to half? Now I care about time, because now I know my half concentration, and now what do? Boom. That blue one now has a half-life at that point. This becomes confusing because I could write a half as a fraction, which then makes me think it's a number. It's a label. It's a half-life. Okay? So we'll change that away from a number, and we'll call it H. How do you spell half-life? HL. What's the half-life for the green one? Well, I do the same thing. I start where I have my max concentration, I go to half. Where's the half going to be? The exact same space, because all I care about is the concentration. So I go to half that concentration, and now I got to go ... to my green one. Where's my half-life? My half-life for the green one is now longer than for the blue one. I'm doing that just based off interpreting that time axis. Kind of makes sense? Okay. How could we leverage this? Carbon-14 takes 5,730 years for the atoms to decay. Why is this valuable? Well, carbon-14 is constantly produced in our atmosphere. So over time, the concentration of carbon-14 is relatively static. So as long as there's carbon-14 coming in, right, we would expect a static concentration. What things react with carbon? Plants. Plants pull carbon dioxide out of the air and turn it into a fuel source. Animals then eat said fuel source. When the animal stops eating, what happens to the concentration of carbon-14?
It begins to decay.
It starts to decay.
Carbon dating.
So now what I can do is look at that dead animal or plant, and I can look at how much carbon-14 is there. Because I know carbon-14 is no longer going into the dead animal because it needs to ingest it to get it, right? I can now somewhat accurately determine the age of that thing. That's kind of cool. That's coming from half-lives. Okay? Which isotope, which reacts at a faster rate? Blue or green?
Blue.
Blue, and how do we know that?
Steeper slope.
Steeper slope. Awesome. Real quickly off the slope. We don't even have to think about half-life, so we can just nail that down. Make sense? Okay, I'll stop yapping at you.